We talked about the overall program and its visualized streams interaction. Let's look at the real fun stuff, the actual code. And the cool part about this is the code is basically just a direct refinement of the visualizations and the design. So let's take a look. You can see here that we've got ourselves a little code. And now notice we've kind of moved from object-oriented world where we had base classes and subclasses and architecture and structure and being able to customize things through overriding methods defined in the base class, blah, 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 all that good stuff. Now we're moving into functional land. And that's exactly the point. We're moving from the architectural perspective into the details of the computation. And as often is the case, the computation is well expressed using functional programming techniques. So here we go ahead and make a method call. This is a hook method defined in the framework that will get the input, which in this case is going to be a list of URLs. So we get that input. We then convert that into a stream. Then we go ahead and we apply filter. So this is going to take a stream of URLs as input, and it'll give you back a stream of URLs that have not already been downloaded, so the non-cached ones. And remember the thing about filter. Filter does a couple interesting things. It doesn't change the type, but it might return a smaller number. In this case, anything that's been filtered will not be returned. Or sorry, anything that's been cached will not be returned. Here's how this actually works under the hood. There's lots of different ways to implement this. This is a very simple way of doing it. This is the URL cached method. You give it a URL, and it goes ahead and it filters out. It goes and checks to see whether an image already exists in the file system or not. And if the count is greater than 0, then it's already there, so we're going to ignore it. And that's why we have to negate the result, because this is just saying, is it cached? And if it is cached, we want to negate it because we don't want to download stuff that's already here. Here's the actual method that does this. It goes ahead and it makes a file with the filter name plus the path name where the image repository resides on the device. And then it encodes it properly, and then it checks to see if there's already a file with that name. So that's what that does. There are obviously other more clever ways of being able to do filtering. Being able to do cache management. In particular, if we were writing a cache in a web environment, we would probably want to check to see whether the content was recent, right? And anybody's ever used a web cache mechanism knows that when you download something from a website, it'll give you back a cache header that'll tell you how long the content is valid. And after a while, it'll basically, it'll time out so that you may have to go down and get a new version. This is typically used in advertisements on websites where they want to have a deal that lasts for a certain amount of time. And so they'll basically download an image with the deal information, and then they'll say, this is only good for an hour, right? So if somebody goes within that time to look at the deal again, it'll be cached. But after that time, they'll have to go and pull a new image. We don't do that here, but you could. OK, then we go ahead and map the blocking download, and that'll convert the stream of URLs into a stream of images. Remember the deal with map. Map always gives you back the same number of items that you took as the input. So output and input are the same. And also remember that map potentially can change the type, as it does here, right? So it goes from URL to image. So the elements count doesn't change, but the type may change. Here's what the code looks like. This is kind of fun. As you can see here, what we do is we have blocking download is a method. We can pass in a method reference. It takes a URL and returns an image. And under the hood, what it does is it goes ahead and calls blocking task call in managed block. If you recall when we talked earlier about the fork join pool, I'd mentioned that it has this thing called a managed blocker. And a managed blocker can be used to temporarily expand the size of the thread pool if something would block. And downloading a big image will definitely block. So download image just goes out and downloads the image across the network. And this makes sure that the thread pool will be temporarily expanded. We covered that earlier. OK. By the way, if you take out that feature, if you don't use managed blocker, then your code typically won't be as scalable, because when it blocks, you won't have any other threads left in your pool to run. blocking download and calling map on blocking download will give you a stream of images. And then what we want to do is we want to go ahead and apply the filters to each image. And as I mentioned before, when we look at this code, apply filters is going to return a stream of images that correspond to the things that have been filtered or transformed. And therefore, we have to flat map them back together again so we don't end up with a stream of streams. Or we end up with a stream, not a stream of streams. Keep in mind that flat map can return greater than, less than, or equal to the number of elements. In this case, it's most likely going to return greater than because it's going to do n filters or transforms for each image. So if you have 2 filters, it'll return 2x. Okay. Here's what apply filters does. You can see that apply filters takes a stream of images. Sorry, it takes an image and it returns a stream of images. And what it does is it goes ahead and it calls parallel stream on the mFilters variable. mFilters is basically something that will keep a list of the filters you want to apply. That'll run all this stuff in parallel. And you can see here we go ahead and we make a filter with the image and we run it, and that will go ahead and apply the filter and then store the result in the file system. Now, a couple of interesting things to note about this. Notice this is an intermediate method, or this is an intermediate operation, and it takes a behavior, and that behavior returns a stream. And notice that there is no terminal operation in this particular method, apply filters. There's just returning a stream. So what that means is that this function will run only when we hit the terminal operation down here. So only when collect is called will the whole stream run, and therefore this flat map and apply filters thing isn't actually going to do anything until it's called at the end when the terminal operation triggers the processing of the stream. And I mention that because sometimes people will try to write code where they'll have and the fancy name for this is lazy evaluation, right? So everything here is lazy until we get down to the terminal operation. And the reason I mention that is sometimes people will write streams code and they will sort of forget the laziness of the stream. And as a result, their code will not run very well because nothing starts to run until you hit the very last terminal operation. So you may have a very intricate stream here with all kinds of calls to functions that return substreams and all this kind of stuff. And nothing will actually do anything until you hit the very last part. And that often leads to suboptimal behavior. So if you write a stream that's very complicated and you run it and you don't really see a big speed up in performance, it might be because you're too lazy in the way the stream is evaluated. And the only reason I know that off the top of my head is when we were doing our instructor implementations of the parallel streams algorithm. I was working with a buddy of mine, Monty, and he came up with one way to do it, and I came up with a different way to do it. And when we first ran the approaches, my version was way faster than his. And he was all demoralized. So I said, well, Monty, let's take a look at this. And when we looked at it, he had been overly lazy in his stream implementation. So it just wasn't very parallel. Once he tweaked it, it was way faster, and it was actually faster than mine. So that pissed me off. So we were battling it out, trying to see who could write the fastest version. And I think he still has the win at this point because his approach was very concise. But the main point of all that is that you have to think through some of these issues. So the reason why I'm mentioning this is sometimes it helps to know how a stream is actually implemented internally when you try to figure out how to debug it to make it run faster, because otherwise you can have surprises. All right, collect is a reduction operation that combines everything into a single result, which in this case is a list of filtered images. And right there, we just print out the result, but you could also display it too. Okay, so that's basically the end of